Okay, last time we actually looked at this beam here, simply supported beam with a concentrated load that was 15 foot over from the left support, had a 20-foot span, and we, through a process of, in a sequence of free body diagrams, we came up with what the functions were for the internal shear, both to the left and to the right, as well as the bending moment to the left and to the right of the applied load. Now if we take those functions and we then plot them, this is the kind of thing, of course, that you'll see, right, that here to the left of that support we have the internal shear is a positive 7.5 kips that turns out in this instance to equal the value of the reaction over here at the left. And then to the right we ended up with a shear that was negative 22.5 kips, and that so coincidentally in this instance happens to meet the value of the right hand support. It won't always look quite that simple, but in this case it does, and there is a direct relationship with these reactions, and we showed that last time with the free body diagram approach. Same kind of thing here with the moment, that we see that it increases linearly as we go away from the point load that is the support and peaks right under the applied load. And so this overall shape is very characteristic for both the shear diagram and the moment diagram. When you have a concentrated force, the shear is going to have regions of constant values that change exactly by the amount of the concentrated force. We showed that last time with the free body diagram. And the moment diagram is going to be this straight line, linearly, positively or negatively sloped situation. Now note something here. The moment is function on the left is 7.5x, and that just so happens, the 7.5, to be the same number and sign as the shear in that region. Likewise, when we go to the other side, the slope of the moment diagram is going to be given by us by this negative 22.5, right? And that just so happens to be exactly the value of the shear over in that segment. Is that just coincidence? What's going on? Well, that's what we're going to find out in this particular lesson, and that is we're going to derive what the shear and moment relationships actually are. This is calculus, but it's beam calculus, so it's really cool. In other words, it's just not calculus for the fun of calculus. It's calculus for the fun of structures, or structural calculus is what we're going to absolutely be doing. All right. So what we're going to find out is we're going to find the variation of the shear and the moment through direct integration, as opposed to doing it through the equilibrium method. That's what we did last time. Okay. And then that's going to build up to something called the graphical method that we're going to show in the next lesson that follows on to this, because the graphical method turns out to be a very quick way to begin to do these things. And of course we do it all not because it's fun, even though it is. We do it because it is needed to go find out the maximum internal values of shear and bending moment so that we can design the beam or assess an existing beam. Right? So what we're going to do is our classic little model where we're going to come along and we're going to take a little tiny differential of the beam. Now a lot of authors will do a finite thing, delta x, and then they'll take the limit eventually. I see no point. Let's just go right to the heart of this thing. Right? So let's pull that little free body diagram off to the side. It's dx long. Okay, and that's of course along the long axis of the beam, so the cross section is coming in and out of the plane of the paper here. And then we got to get on there all the various pieces. Right now we actually have a load on here, a distributed load, not a concentrated one, but a distributed one that may vary over its length. We're going to do our first approximation here and assume that it is constant over its length. Now another thing here is I'm using the symbol W. Some people like to use the symbol lowercase q, and there's probably some other common symbols. I use W. Some people say that's omega. No, it's W. Omega is reserved for something else, natural frequency. It's not omega, it's just a W. Right? It's the distributed force per length. And note also, I'm going to use calculus here in terms of my sign convention globally. That to the right is positive and to the and upwards is positive, so my y is showing positive up, even though most of my perpendicular to the long axis of the beam loads are gravity loads and acting downwards. I'm going to call this positive to be consistent with math. Now our internal sign convention says on the left side of the beam segment positive shear is up, and on the right side positive shear would be down. Now because this is differential stuff, the shear on the right will equal whatever it was on the left plus a tiny change. Right? So this isn't some just generic calculus. Math people are being weird and they're being a pain. No. This is saying the shear on the right is equal to whatever it was on the left plus some sort of change. It might be negative, it might be positive. That's what that really means there. Right? Likewise with the bending moment, which will show in the positive direction, m on the left and m plus dm on the right. Right? And let me do one more thing here. This m and this v are the values of the internal forces at a distance x. So x is over here to the left edge. It doesn't really have to be, it's just you have to choose one, and I choose it to be on the left edge. Alright, from here after, we apply the other tool we have in statics. Right? The first tool is the free body diagram, the second tool is equilibrium. And gee, what were we after anyways? Well, differential relationships between the load, that would be the W, the shear, that's V, and the moment, that's M. That's what we're trying to get to here. Right? So let's try this. Let's sum forces in the Y. Let's take upwards positive for the fun of it. We'll have V plus and then W. Well, that's a distributed load, so I have to multiply it by a length. That would be dx in this case to get a load, not a load intensity, but a load. And then notice over here minus V plus dV. Right? Remember, V is the shear at x, and so V plus dV is the shear at x plus dx. Right? And this is equilibrium, so set that all equal to 0. Well, notice that the v's cancel out, and we'll have then that after rearranging dv, that differential will be equal to w times dx. Wow! The incremental change in the shear is equal to the load times, well, that makes sense. We just added this little bit of load on there, and we found out before a concentrated force would create a sudden change in the shear, and that's all that's happening here, except for it'll be a smooth change, because look what we really find out. dv dx equals w. The rate of change, this is so important, we got to write it down. The rate of change of shear equals the load intensity. That w being 5 kips per foot, that would be a very large W, by the way, is not just some load, folks. That is how fast the shear is changing over a foot. 5 kips per foot. Every foot it changes again by another 5 kips. Right? Rate of change of the shear is equal to the load intensity. The change, not the rate, but the change in shear, that would be delta V. Well, that's just going to be equal to the integral of dV over 2 places, which is equal to the integral over that little domain of W times dx. Wow! Well, that makes sense too, doggone it, because hey, W times a length is the amount of total load, and the shear is just going to change by that total amount of load. That actually makes perfect sense here. Right? Now, more generally, what you see is that V as a function of x is equal to the integral of dV, which is equal to the integral of W dx. This would be the indefinite. So 0 to some general value of x. Right? So I've got one specific one. This one is a little bit more general, as written there. Okay. This one right here is going to be your key. And notice something here, dv dx equals w. If you had defined w as going positive downwards, you would have had to put a minus sign right there to get the internal sign convention to work out. Okay, that's the only difference that would happen. All right, now let's do sum of moments about, let's do it about the right hand side, call it 0.0, and I think we'll take clockwise positive. And what are we going to get there? A whole lot of stuff, right? We're going to have the m. I'm going down a line because that way I won't run into that stuff right here. M plus v times this moment arm, that's times dx. Even though that's small, it's not 0. Plus w times dx, that's the total force that effectively acts at that centroid. And remember, we're really not including the variation of w across there. That was already a small approximation. But hey, it was w times dx, and the moment arm will just be dx divided by 2. And then, well, v plus dv goes through this point, so we'll just have minus that quantity m plus dm, and set that equal to 0. Alright, well, those m's cancel out, and again rearranging, what we're going to get is that dm is equal to then v dx plus w times dx times dx over 2. Now what I say in class is I always ask everybody, hey, how big is dx? And they're like, what do you mean, how big is dx? We all know it's super small. Or what do you, this is a trick question. It's like, no, eventually I get them all to say, dx is really small. And I say, okay, so what is dx times dx? And they're looking at each other saying, what? Dx is really small, so really small times really small is really, really small. And hey, what would be really, really small divided by 2? Well, that would be super tiny. Hey, maybe we could just ignore that. And when we do that, we say that that's approximately 0, we end up with first order theory, right? Because first order means to the first power, and dx squared would be to the second power. We're going to end up with that dm dx equals v. That's our second equation in our family of beam statics equations from a differential approach. And that's going to be kind of the same thing we had before. It says that the finite change in the moment then is just going to be the integral of dm, which is going to be the integral of v dx, because dm is equal to v times dx. And more generally, our moment function is just going to be our integral of dm, or the integral of whatever the shear function is. How about that? And what does that really say in words? Well, the rate of change of the moment is equal to the shear. Wait a minute, shear is not just internal force. It's actually got units. It's got units of kip feet per feet. Well, we never express it that way. We just say the shear is equal to 20 kips. No, it's equal to 20 foot kips per foot. The foot goes away, denominator and numerator, right? But it really, the shear is not just a force. It is the rate of change of the moment caused by this shear times that little tiny moment arm. That's why the moment will increase or decrease correspondingly, right? And there we've got the change in moment already talked about. These differential relationships, dv dx equals w and dm dx equals v, or you could write this as one second order differential equation that the second derivative of the moment equals the load, is going to be exactly what we need in our to create our family of beam equations. Well, it turns out that for statics, that's it. We're missing beam kinematics, and we'll get that in the mechanics of materials course, and then we'll have a fully populated family. But here you go. There's our family crest, and we got the first 2 generations of it right there. Isn't that pretty cool? Alright, in the next videos we're going to go find out how to apply all that.